Okay, so let's look at our first example of a conformal transformation. And what this conformal transformation will do, it's going to map the plane, the infinite plane, into a sphere. We might say the unit sphere. Okay, so let's now define this conformal mapping. Now I'm going to define it with a drawing, and I'm sorry, my drawing skills are not very good. So rather listen to what I'm saying than look too much at the picture. The picture's not going to be good enough to understand without my explanation. Okay, so here is the infinite plane. So I want it as a 2D surface. So I'm drawing these two lines like this. This is part of a 2D surface, but I'm also going to draw it looking side on. So maybe that will give you a better idea to understand what we're doing. So there is the plane side on. And now what I'm going to draw is I want a sphere. So let's draw the sphere. Here is our sphere. Okay. And the south pole of the sphere sits at the origin of the plane. So if I'm looking side on, the sphere just looks like a circle. So this point over here, which is the origin of the plane, corresponds to this point over here. And now how do I define the map between the plane and the sphere? Well, let me draw it in the simpler diagram first of all. So there's also a north pole here. So there's the north pole. And to define the mapping, I draw a straight line from the north pole down to the plane. And this line obviously strikes the plane at a point. So there is a point on the plane, and it pierces the sphere at a single point. So here is a point on the sphere. And what the map does is it takes that point on the plane, this point sitting over here on the plane, into this point over here on the sphere. So by drawing this line through the North Pole, I've associated a point on the sphere to a point on the plane, and that's the map going from the plane to the sphere. Okay, so now let's do exactly the same thing, but in 3D. So again, I've got a North Pole. I come down towards the plane. So I get to some point in the plane. So that's this black cross sitting over here. That's a point in the plane, and it will pierce the sphere at some point. So this point on the sphere is taken to that point on the plane. Okay, so now I want to be a little bit more ambitious. So look at this red little segment over here, okay? What is this red little segment over here on the sphere? Well, I start, of course, from the South Pole, and then I start to lift up. And the further I go along this segment, so the further I lift up the sphere, and I keep going. And if I went in the opposite direction, well, now I start to climb over on the back of the sphere. And I'll climb all the way up to the North Pole and down again. So as I'm going off to infinity, I get closer and closer to the North Pole. And to show you why that's the case, well, let's come back to this 2D picture over here. As I go further and further along the plane, so now I've mapped to a more distant point on the plane, I get to a point on the sphere that's closer to the North Pole. And if I keep going to more and more distant points, so this would be a point that's actually off the iPad, then I again get closer to the North Pole. And to really get very, very close to the North Pole, then I'll have lines that are almost parallel to that black line at the bottom there. So they become points which are very, very, very far away. And of course, it works on both sides. Okay, so as I move further and further along the plane, I get higher and higher on the sphere. And that's what's happening with this red line. As we move out along the red line, so so as we move out on the red line on the plane, so the red line on the sphere inches up towards the North Pole. And well, it's not just for that red line. Okay, so let's now look at this gold line over here. And this gold line would now start to stretch like that. Oh, my drawing is terrible. Then we come down again and we come back towards the origin. So all of these lines that have, let's pick another color. I don't know, let's go for this. So we'll do that. Good. So, for example, if we had another straight line over here, this would be another line of longitude on the sphere. Okay. Oh, this drawing is bad. I should probably have drawn. So that lilac line shouldn't really be there. That's more like a lilac line going over here. Okay, some angle like that. So all of these straight lines going radially out in the plane, they correspond to lines of latitude on the sphere. We could also ask, well, what would happen to a circle? So let's draw a circle here on the plane. So this is a circle on the plane. So this is on the plane. Now, notice that we're not going away from the origin. So we're going to get a circle on the sphere, which corresponds to some fixed distance from the South Pole. And one thing that you could notice here, so hopefully I'll be able to draw it, is that here there's a 90-degree line between this yellow line and the red line. And on the sphere sitting over here, this is also a 90-degree line because you've got a line of latitude and a line of longitude. So this 90-degree between the two lines has been preserved, okay, from the plane to the sphere. So this is what I said a conformal map would do. It preserves the angles between lines. It also takes lines to lines, spheres to spheres, circles to circles, but it can take lines to circles. A conformal map is allowed to do that. What does it mean to map the plane to a sphere? Well, it means, in fact, that you must be studying functions of a specific type, okay? So this is called the one-point compactification of the plane. What does a one-point compactification of the plane mean? Well, if you walk off to infinity in this direction, or you walk off to infinity in that direction, or any other direction along any of these lines, then on the sphere, you're always getting up to the North Pole. So you're always walking to the same point. So when you look at these functions on the plane that you're studying, they must be functions that go to a specific constant value as you walk off to infinity. And it doesn't matter whether you walk off to infinity in the direction of this red line, or the direction of this yellow line, or the direction of that yellow line. Any direction that you walk off to infinity, you must always get the same value for the function because you're always landing up at the North Pole, this n here, on the sphere. Okay, so that's what it means through the one-point compactification of the plane. What you're really doing is stating what class of functions you're looking at, and it's the class of functions that goes to some fixed value as you walk to infinity in any direction. So the value you get for your function doesn't depend on the direction in which you walk off to infinity. Sorry, my drawing skills are so bad. I hope you can see what's going on. Now let's try to write down some sort of a formula. So let's call this the x-axis. Let's call this the y-axis. We'll introduce a complex coordinate z is equal to x plus iy. And now let's write down a concrete formula for this mapping. Okay, we'll do that in a moment.